Hello, today we are going to discuss the critical temperature, its significance, the derivation of the expression of critical temperature from Van der Waals equation. This is actually under the topic the liquefaction of gases. Let's start. In the year 1869, Thomas Andrews found isotherms, which is actually a graph of PV. This is known as isotherm. First of all, we draw the isotherm. The figure is actually the Andrews isotherm. This is Andrews isotherm. Isotherms, there are more than one graph. So this is actually the graph of P versus V, pressure and volume of different state of substance. Now, say this is our point A, this is our point B, this is our point C, and this is our point D. Now, say this isotherm actually for temperature T1, this is for T2, this is for Tc actually, and this is for T4. We can write it as T3, and this is actually Tc. Okay. Now at the temperature T1, there are actually three phases of the substance. Here in the CD portion, this is actually the vapor phase, because the temperature and volume related. As the volume decreases, the pressure increases. But in the portion AB, the pressure abruptly increases, the volume is decreased in very negligible amount. So this portion actually liquid, this portion actually vapor, and in this portion B.Sc, actually liquid and vapor exists at equilibrium. Sometimes this is known as metastable state. Okay. Now as the temperature increases, definitely we can write that T1 temperature is less than T2. This T2 temperature is less than T3, and T3 temperature is less than T4. Okay. So as the temperature increases, this portion, this metastable state actually contracted. And at the temperature T3, these two states actually coalesce to a certain point. Say this point is designated as O. This particular point is known as critical point. Now let us discuss some significances of this point. This is actually critical point. At the temperature at which the critical point is found, the critical point is observed, is known as critical temperature. And the corresponding volume is known as Vc. This corresponding volume is known as Vc. This is critical volume, and this particular pressure, the corresponding pressure, is known as Pc. This is our critical pressure. So the critical temperature is actually defined as the temperature, the highest temperature at which the liquid state can be, the vapor can be transformed into liquid. The vapor can be converted into liquid. Above the critical temperature, a vapor can't be converted into liquid, or rather it can be said that the gaseous substances can't be transformed to liquid above the temperature of Tc. This is your critical temperature. Now let's have features of the critical point. Some features, let us point out Some features of critical point. Critical point. Number 1, look at this point O, at the critical point, actually the vapor phase and the liquid phase coexist. That actually the gas and liquid coexist at this temperature, at this point, because after above this temperature there is no existence of a vapor. The vapor is converted into gas. So the feature of critical point is above the critical temperature, above the critical temperature or critical point, above the critical temperature, vapor is known as gas. Is known as gas. Number 1. Number 2 is at this point there is no difference between gas and liquid, because these two phases exist at this point. So the surface of separation between liquid and gas disappears at this point. So we can note down at the critical point, the surface of separation between gas and liquid disappears. Thirdly, at this temperature, I can say again, at this temperature there is no difference between gas and liquid. So some physical properties like density, refractive index at this point of liquid and gas becomes equal. So at the critical point, density, refractive index, etc. of gas and liquid become equal, become identical. Okay. Our next point, above the critical temperature, a gas can't be transformed into liquid, because for gases the PV graph is like rectangular hyperbola, and at the temperature T4, not at T4, above the temperature Tc, actually gas phase exists. So above critical temperature, Tc, gases can't be transformed into liquid. So critical temperature is the highest temperature at which the vapor can be converted into liquid. Next point, number 5. Look at here. Above the critical point, actually the kinetic energy of the gas molecules increases. and below the temperature of below the critical temperature, the molecular attractive force among the liquid state, among the molecules in the liquid state increases. So at this point, these two actually becomes equal. Which two? The molecular attractive force between the molecules in the liquid phase and the kinetic energy of the gas molecules in the gas phase. So we can point out at the critical point, the intermolecular attraction among the molecules in the liquid phase becomes equal to the average kinetic energy of the molecules in the gaseous phase. So we can say at this point the gaseous molecules possess the kinetic energy which is the lowest value of the kinetic energy, because this is the kinetic energy acquiring which the molecules can exist in the gaseous phase. So this kinetic energy is known as threshold kinetic energy. The molecules must possess this threshold kinetic energy to exist as gas. Okay, so the kinetic energy of the gas molecules in the we can note down, or 0.6. We can note down, or 0.6. The kinetic energy, the average kinetic energy, definitely the kinetic energy possessed by the gas molecules at the critical point is known as threshold kinetic energy. Threshold kinetic energy, which must be possessed by the gas molecules to exist in the gaseous phase. Threshold kinetic energy. Okay, so these are actually the features of the critical point. Next we are going to derive the expression of critical temperature for van der Waals gases or real gases. Okay. Next, we are going to derive the expression of critical constants. The expression of critical constants. Critical constants. Actually, the critical pressure, critical volume and critical temperature, these are collectively called critical constants. Now we know van der Waals equation for 1 mole of any gas, 1 mole of a real gas, P plus A by V square into V minus B, this is equal to RT. Okay, next P equal to RT by V minus B, RT by V minus B minus A by V square. So for example, this is our equation number 1. This is our van der Waals equation actually. Now look at this point, the critical point. At this point the slope of PV graph is 0. So we can write that is del P del V at constant temperature Tc is equal to 0. So we can take the derivative of this equation, that is del P del V at constant T. This is equal to, keeping temperature constant, we can take the derivative of P with respect to V. So T is constant, this is RT minus RT by V minus B. This is by V minus B whole square plus 2A by V cube. Okay, we take the derivative of V is a variable here. So this is our equation number 2. Then again, look at here, we can take the second derivative, second order differential, del square P del V square at constant T equal to minus and minus plus, this is 2RT by V minus V whole cube minus 3 into 2, this is 6A by V to the power 4. This is our equation number 3. Okay. Now, as I say, at the critical point, this slope is 0 and definitely this one is also 0. Why this one is 0? Because look at here, for the gaseous phase, this is the maximum point, this is the maxima, and for the liquid phase, this is the minima. And now when these two phases actually coalesce at the point O, this maxima and this minima becomes equal. So actually this del square P del V square at constant T, this is also 0 because maxima and minima points coincides. Okay, so this is also 0, this is also 0 when the temperature is T equal to Tc. Now we can write at the critical point, or critical temperature, at the critical temperature, that is at T equal to Tc, del P del V at constant T, this is equal to 0, and again del square P del V square, that is Tc at the point Tc, this is also equal to 0, right? Okay, now we have from equation number 2 and equation number 3. Now this one is 0, so equation 2, the right part of the equation 2 is 0. This gives us equation 2 implies RT by, not RT, this is RTC at the critical point Tc, RTC by V minus B whole square, this is equal to 2A by Vc, because at the critical point this V is actually Vc. And equation 3 implies, equation number 3 implies equation 3 implies this portion is actually 0. So 2RT by V minus B whole cube, this is actually 6A by V to the power 4. We can write not V, these are actually TC, this is VC, this is again VC. Okay, this is our equation number 4, and say this one is equation number 5. Now if we divide equation number 4 by equation number 5, equation number 4 divided by equation number 5 implies what? RTC, equation number 4, this is VC minus B. There is a 2 factor. Okay, equation number 4 divided by equation number 5 gives us VC by B by 2. This is equal to 2A. A is cancelled out, so 2 by 6, 2 by 6, sorry, here is a cube here. Okay, 2 by 6, question number 5, this is into VC. Okay, so this gives us this is VC minus B. This is equal to 4 by 6 into VC. This is actually 2 by 3 into VC, gives us 2 by 3. This is 1/3 VC is actually B. This gives us VC equal to 3B. This gives us VC equal to 3B. Okay, this is the critical volume of van der Waals gases. Critical volume of van der Waals gases. Next, we want to derive the equation of TC. Now, substituting the value of VC at any of the equation number 2 or 3, we can write substituting the value of, here it is VC, substituting the value of VC in equation number 4. Equation number 4 implies RTC by VC is actually 3B, so this is 3B minus B whole square equals to 2A by 3B whole cube. This gives us RTC by, this is 2B whole square, this is 4B square, equal to 2A by 27B cube. This gives us TC equal to 4 into 2, B square is cancelled out, B is here, so TC equal to 8A by 27 RB. 8A by 27 RB. This is the expression of critical temperature, 8A by 27 RB. Okay, it is right. Okay, next we have to find the value of PC. Look at here, at the critical temperature, the temperature is TC, volume is VC, and the corresponding pressure is PC. So we can write van der Waals equation we can write van der Waals equation at the critical temperature. Now we can write the van der Waals equation at the critical temperature. Pc equal to RTC by Vc minus B minus A by Vc square. Okay, this implies Pc equal to RTC by Pc equal to, substitute the value of Tc here, R into 80 by 27 RB. 27 RB. Vc is actually 3B. Vc is actually 3B. 3B minus B minus A by Vc is 3B whole square. Right? Next, R is cancelled out from here. So here is 2B. So 8A by 27B into 2B here minus A by 9B square. Okay, this is actually 8A by, this is actually 4A, this is 4 by 27B square minus A by 9B square. LCM is 27B square, gives us 4A minus 3A. This is nothing but A by 27B square. This is the expression of critical pressure PC for van der Waals gases. So these are three expressions. This is Vc, this is Tc, and this is Pc. Critical temperature, critical volume, and critical pressure. Now we know compressibility factor. We know compressibility factor Z. Compressibility factor Z. Compressibility factor. Compressibility factor Z. Definitely at the critical temperature, at the critical point. Z equal to PC Vc by RTC. This gives us, by substituting the value of Pc, we have A by 27B square, B is 3B, R into Tc is 80 by 27 RB. This gives us 3 by 8. Look at here, except 3 by 8, everything is cancelled out. Okay, so Z equal to 3 by 8. This is at the critical point. At the critical point. At the critical point. Now there is another term, the critical coefficient. There is another term, critical coefficient. Sorry, critical coefficient. This is actually equal to RTC by PC into Vc. This is the reciprocal of Z. This is nothing but 8 by 3. This is known as critical coefficient. Now, in the competitive exams, there are some questions related to the critical temperature of different gases. Let us take some example. of different gases, we know our guideline is critical temperature Tc, this is equal to 8A by 27 Rb. So we can write in this way that Tc is proportional to nothing but A by B. Okay, now let us take some examples of different gases. Say some gases like H2O, H2O means H2O vapor definitely, ammonia, say for example nitrogen, oxygen, say for example methane, maybe hydrogen, maybe helium. In competitive exams, we have to arrange 2 or 3 or 4 gases in the order of their critical constants, critical temperature. Okay, so the order of critical temperature, so the order of critical temperature of these gases, order of critical temperature of these gases. First of all, we write the order and then explain it. Firstly, this is water, next it is ammonia, so there may be carbon dioxide also, there may be CO2 also, next come CO2, next it is your methane, then it is oxygen, then it is nitrogen, then it is hydrogen, and lastly it is your helium. So how can we explain this order? Say in case of water there is lot of hydrogen bonding. So hydrogen bonding, the intermolecular attraction force is the type of intermolecular attraction force which is greater than ammonia, because in water there is hydrogen bonding, in ammonia molecules there is also hydrogen bonding, but oxygen is more electronegative than nitrogen, so the hydrogen bonding is greater here. So the intermolecular attraction force in water is greater. So to transform the liquid water in the vapor phase, in the gaseous phase, greater temperature is required to convert the water, liquid water into vapor. So critical temperature of water maximum. In case of carbon dioxide, if the structure of carbon dioxide is like this linear structure, there is some dipolar interaction, del plus, this is del minus, this is another molecule of carbon dioxide, this is del plus, this is del negative. So there is a weak interaction, this is known as dipolar interaction, which is present in carbon dioxide molecules. So the critical temperature of carbon dioxide is lesser than ammonia and water, where hydrogen bonding was present. In methane there is some van der Waals attraction which is weaker than this dipolar interaction. In case of oxygen and nitrogen, we know from molecular orbital theory this oxygen is paramagnetic in nature, but nitrogen is diamagnetic. So the repulsive force between the nitrogen molecules, because lone pair of nitrogen here, repulsive force between or among the nitrogen molecules is greater. This lone pair, there will be repulsion. This lone pair, there will be repulsion. So the intermolecular attraction forces of nitrogen is lesser than that of oxygen. And of course in hydrogen there is no such effect, and in case of helium it is a monoatomic gas, so the intermolecular attraction force is minimum here. So we explain this order with respect to the intermolecular attraction force. We know A is the measurement of intermolecular attraction forces among the molecules, gas molecules, and B is actually the size of the gas molecules. There is no large difference in size of the molecules except helium or hydrogen. The size of the molecules almost same. So the determining factor is here is the molecular attraction forces, as I explained. So as the molecular attraction forces increases, the critical temperature increases. So this is the order of critical temperature for these gases. So this is all about our critical temperature, critical point, etc., or liquefaction of gases. Thank you for watching the video.